Let's talk pyrimidine biosynthesis. So here we're going to have a 6-step process, folks. 2 ultimately, UMP at the end of the first part. Then we'll convert UMP to UTP, and just one more step to CTP. Then it gets a bit more complicated from there, you'll see. This is less complex than purine biosynthesis, just one ring, right? But we again have multiple rate determining steps, step 1 and step 6, and then again a large protein complex made from enzymes 1, 2, and 3 of this pathway. Let's do steps 1, 2, and 3. So the first step is performed by carbamyl phosphate synthetase 2. Here we are going to get the N3 nitrogen from a glutamine. We've seen that already. We're also going to get carbon 2 from bicarbonate. And this is interesting, folks, because this reaction uses 2 ATPs. Well, one of those ATPs powers the reaction, right? Remember, these anabolic pathways use energy. But the other ATP provides the phosphate of carbamyl phosphate. Up next, aspartate transcarbamylase, often referred to as ATCase. It performs a condensation reaction, and using aspartate, we add the N1 and C4 through 6. So there's the atoms we need, right? And that addition gives us this. Chunk of aspartate added on there. Step 3, performed by dihydroorotate. Here we're having an intramolecular condensation. We've seen this before, right? We know that pyrimidines need to be cyclic in nature, so in this step we cyclize. What about the back half, getting us to UMP? So step 4 is performed by dihydroorotate dehydrogenase. We see the word dehydrogenase, we should know a redox reaction is happening. And this reaction is interesting because it happens at the inner mitochondrial membrane. That's different. All the other steps that are happening here, folks, are happening in the cytosol. But in this step, we do the redox reaction using a quinone. And so we know there is a large quantity of quinones at the inner mitochondrial membrane. Think of the CoQ used as a part of the electron transport chain, right? We could use those quinones to perform this oxidation. And so you can see the oxidation happened in this step. Step 5, performed by orotate phosphoribosyltransferase transferase. Oof. So up until this point, unlike purines, we haven't had the ribose attached. So step 5 uses PRPP, right? I told you we were going to see it again, to add on the ribose group and again fix the anomer to the beta anomer. Step 6, performed by OMP decarboxylase. It's named fairly well, right? It performs a decarboxylation where we lose the carbon dioxide that was there. And that gets us to UMP, the uridine monophosphate. Now, at this point, we need to take a slight tangent, folks. So how do we get to CTP? Well, CTP first has triphosphate, right? And we just made what? UMP, monophosphate. So we first need to just get more phosphates on there. These reactions are performed by various nucleoside monophosphate or nucleoside diphosphate kinases. These kinases are specific to their base. So the substrate will be the adenosine or the uracil, right? The substrate is specific. But the other substrate that is used to add a phosphate doesn't matter, which is kind of weird, right? So all of these enzymes are indiscriminate of their source of phosphate. So they could use ATP to get an extra phosphate to make CDP for CMP or CTP from CDP. Doesn't matter where that phosphate comes from. Additionally, these enzymes are indiscriminate of the ribose versus deoxyribose form of the nucleotide. Okay, so let's say now we had converted UMP to UTP by just adding some phosphates through a kinase. That is performed by CTP synthetase. And we've seen this before. We're using a glutamine to donate an amino group and replace the keto functional group with the amino, forming CTP. What have we seen here, folks? Well, we've seen kind of the same patterns repeating. We saw some ATP used in this process, not quite as much as in purine synthesis, but again, we saw the glutamine, we saw the aspartates being used either in whole or in part, specifically for amino groups. We saw bicarbonate, we saw PRPP show up again, and we saw a quinone being used as a redox cofactor. Up next, we'll talk through regulation of this pathway. Then we'll talk a little bit more about deoxyribose versus ribose. And finally, you're probably wondering where thymidine was going to come in. Up next.